Hello there, and welcome to the Calm Science Sleep channel. I'm Jeffrey, and so glad you found your way here. Maybe it's been a long day, or maybe you're the kind of person who likes to fall asleep thinking about the deepest questions anyone has ever asked, the ones with no easy answers, the ones that live at the edges of everything we know and drift quietly into the unknown beyond. Either way, this journey is for you. Tonight, we're going somewhere unusual. We're not visiting a planet, or drifting through a galaxy, or exploring the ocean floor. Tonight, we're going further back than any telescope can see, further back than the first stars, further back than the first atom, further back, even, than time itself as we understand it. Tonight, we're asking one of the oldest and strangest questions a human mind can hold. What existed before the universe? It sounds simple at first, and then, gently, it opens into something vast, something that has occupied the minds of physicists, philosophers, mathematicians, and dreamers for as long as people have been asking questions at all. And the wonderful thing, the thing that makes it perfect for a night like this, is that the answer isn't settled. There's no final page to turn, only ideas, each one beautiful in its own way, unfolding slowly in the dark. So let your body settle. Let the tension in your shoulders soften. Let your breathing find its own quiet rhythm. There's nothing you need to hold on to tonight. No answer you're required to reach. We'll move gently from one idea to the next, and if sleep finds you somewhere in the middle of it all, that's exactly right. Let's begin. The universe, as best we can tell, is about 13.8 billion years old. That number is staggering on its own. But what it really means is that there was a beginning, a moment before which we cannot clearly see, a point at the edge of our knowledge where the tools we use to understand the cosmos simply stop working. We call it the Big Bang. But that name is a little misleading. It wasn't an explosion in the way we usually imagine one. There was no empty space for it to explode into. Space itself didn't exist yet. Time itself, according to most of our best models, didn't exist yet either. The Big Bang wasn't something that happened inside the universe. It was the event from which the universe emerged, along with everything we use to describe events at all. And that's where things get wonderfully strange. Because when we ask, what came before the Big Bang, we may be asking a question that doesn't quite have a grammatical answer. We're reaching for a time before time, a place before place, a story before stories were possible. And yet, scientists haven't stopped asking, because even at the very edge of the knowable, there is something worth looking for. For most of human history, the question of what came before the universe was left to mythology and religion. Every culture that has ever existed has had some answer, some story, some image. Many of these stories share surprising similarities: a void, a stillness, a breath, a word, a God that was always there. These weren't failures of imagination. They were the first attempts to reach into the dark and bring something back. The ancient Greeks imagined chaos as the formless beginning. Not chaos as we use the word now, meaning disorder, but chaos in its original sense, a vast primordial emptiness from which everything else emerged. One Greek poet described it as a yawning void, a gaping nothing that preceded the gods themselves. In Hindu cosmology, there is a concept called the Brahman, an eternal, infinite, unchanging ground of being. The universe arises from it, exists within it, and eventually dissolves back into it, only to arise again. Not once, but endlessly, in cycles so vast that the numbers used to describe them make the age of our universe look like a single breath. The Norse myths imagined a great emptiness called Ginnungagap, the yawning void, existing before creation. Cold and hot, ice and fire, meeting at the center until the first being stirred. These images, the void, the cycle, the eternal ground, the meeting of opposites, didn't disappear when science arrived. They transformed. They became equations. They became theories. They became the quiet obsession of some of the most brilliant minds of the last century. And what those minds have found is extraordinary. One of the earliest scientific ideas about what preceded the universe came from a man named Georges Lemaitre, a Belgian priest and astronomer who, in the 1920s, proposed something remarkable. He looked at the universe expanding around him and ran it backward in his mind. If everything is moving apart now, then long ago, everything must have been much closer together. Go back far enough, and all the matter and energy in the universe would have been compressed into something unimaginably small and hot. He called it the primeval atom, a single point from which everything began. When Albert Einstein first heard Lemaitre's idea, he reportedly told him that his mathematics was correct, but his physics was abominable. Einstein himself had added a term to his own equations, the cosmological constant, specifically to prevent them from predicting an expanding universe. He believed the cosmos was static and eternal. A beginning seemed philosophically uncomfortable to him. But Lemaitre was right, and eventually, the evidence became undeniable. In 1929, Edwin Hubble confirmed that galaxies were moving away from us in every direction. The further they were, the faster they receded. Space itself was stretching. The universe was growing. And if it was growing, then it had once been smaller. If you ran it all the way back, you arrived at a beginning. Einstein later admitted his cosmological constant had been his greatest blunder. Though, as it turned out, the universe had something else in mind for that term entirely. But that's a story for another night. What matters here is that the idea of a beginning was now in place. And with it, the question that has haunted physics ever since. What came before? One answer, perhaps the most unsettling of all, is that the question itself may not make sense. Stephen Hawking, one of the most celebrated physicists of the 20th century, proposed something called the no boundary proposal, developed alongside his colleague Jim Hartley. The idea is elegant and strange in equal measure. It suggests that asking what came before the Big Bang is like asking what is south of the South Pole. There is no south of the South Pole, not because something is blocking the way, but because the South Pole is the southernmost point. There is no further south to go. The question has no answer, not because the answer is hidden, but because the concept doesn't extend that far. Hawking and Hartley proposed that time, near the Big Bang, behaves differently than we experience it now. In their model, time near the beginning of the universe becomes more like space, smooth, bounded, without an edge. There is no single moment of creation, no point at which you can point and say, here, before this, there was nothing. Instead, the universe simply is, in a way that has no clear before. Hawking described it this way. The boundary condition of the universe is that it has no boundary. The universe would just be. Not the creation of a god or a cause, but a self-contained mathematical structure. A finite reality with no beginning in the conventional sense. It is a deeply strange idea, and whether it is the right one, we don't yet know, but it offers a particular kind of peace. The universe doesn't need a before. It contains its own completeness. Still, not everyone is satisfied by that answer, and science is rarely content with one possibility when several remain open. Another idea, perhaps the most mind-bending of all, comes from a physicist named Alexander Vilenkin, who developed a concept called quantum tunneling from nothing. In quantum mechanics, particles can do things that classical physics says should be impossible. They can pass through walls. They can appear on the other side of barriers they shouldn't be able to cross. This is called quantum tunneling, and it is real. It happens constantly in the cores of stars, inside your own cells, in every semiconductor device you've ever used. Vilenkin asked a wild question. If quantum tunneling allows particles to appear from nothing, in a sense, could the universe itself have tunneled into existence from a state of absolute nothingness? In his model, there was once literally nothing. Not empty space, not a quantum vacuum, not a dark sea of potential. Nothing. No dimensions, no time, no energy, no laws. And then, through a quantum fluctuation, a universe appeared. Not because something caused it, but because quantum mechanics permits it. And if something is permitted by the laws of physics, it will eventually happen. But here is where the thought becomes recursive. If there were no laws of physics, how could quantum mechanics permit anything? Vilenkin's answer is that the laws themselves are what tunneled into existence. The universe arrived complete with its own rules. A self-bootstrapped reality, conjured from absolute nothing by a fluctuation that preceded the concept of fluctuations. It is the kind of idea that, if you hold it too tightly, gives you a headache. But if you hold it loosely, in the soft way you hold a thought just before sleep, it has a kind of luminous beauty to it. Something from nothing. Creation without a creator. The first word spoken by no mouth. There is another possibility, quieter and older in some ways, that the universe didn't come from nothing at all. That nothing never existed. That existence is the natural state, and what would require explanation is emptiness. Some philosophers have argued this for centuries. The German philosopher Gottfried Leibniz asked the fundamental question directly in 1714. Why is there something rather than nothing? He believed the answer pointed toward God, but the question itself has outlasted any particular answer. Some modern thinkers suggest that nothingness is actually unstable, that a true void, a state of absolute non-being, would be somehow less stable than the existence of something. That being is, in a deep sense, easier than nothing. This is not a proven claim. It may never be, but it carries a strange resonance. The universe is here. Whatever the alternative was, it didn't last. One of the ideas that has captured the imagination of physicists most powerfully in recent decades is the concept of the multiverse, and within that, a particular version called eternal inflation. In the 1980s, physicist Alan Guth proposed that the very early universe went through a period of extraordinarily rapid expansion called inflation. In the tiniest fraction of a second after the Big Bang, space expanded faster than the speed of light, smoothing out the early cosmos and planting the seeds of all future structure. Inflation explained several puzzles about the universe that had long troubled cosmologists. Why does the universe look the same in all directions? Why is it so flat? How could regions of the cosmos that have never been in contact with each other look so similar? Inflation answered all of these elegantly. But inflation had an unexpected consequence. Andre Linde, one of the architects of inflationary theory, realized that inflation, once it starts, may never fully stop. Most regions of space eventually stop inflating and become universes like ours. But the inflationary background keeps going, driven by quantum fluctuations that produce new inflating regions endlessly. Each one becomes its own universe, expanding and evolving independently. And the process is self-sustaining, eternal. In this picture, the question of what came before our universe has a kind of answer. Before our universe, there was inflation. Not the inflation of our universe, but the larger inflationary background from which our universe arose. A seething quantum foam of potential from which bubble universes pop into existence and expand into their own separate realms, each one potentially with its own physical laws, its own constants, its own story. Our universe, in this picture, is one bubble among an uncountable number, born from a larger sea, not the first and not the last. The physicist Alan Guth has described the multiverse as the ultimate free lunch. The universe appears to get something from nothing, but that something was borrowed from a quantum background that is itself eternal. No beginning, no end, just an endlessly proliferating foam of realities, each one full of its own light and darkness, its own stars and questions. This is called eternal inflation, and it remains one of the most widely discussed ideas in cosmology. It is also, by its nature, extraordinarily difficult to test. If other bubble universes exist, they are beyond our cosmic horizon. Their light, if they have light, cannot reach us. They are forever separated from us by the expansion of the multiverse's inflationary background. But some physicists have speculated that under certain rare conditions, two bubble universes might have grazed each other in the distant past, leaving a faint mark in the cosmic microwave background, the ancient light of our own Big Bang. Searches for such marks have been made. So far, nothing definitive has been found. But the search continues. There is another framework, very different in character, that offers its own answer to the question of what came before. It comes from an ancient tradition of thought, though one dressed now in the language of modern physics. Cyclic cosmologies. The idea of a cyclic universe, one that expands, contracts, and begins again, is extraordinarily old. Hindu philosophy contains it. Greek thinkers proposed it. Friedrich Nietzsche, in a different context entirely, imagined what he called eternal recurrence, the idea that all things repeat infinitely. These ideas were more philosophical than scientific, but in recent decades, physicists have tried to build rigorous models that capture this intuition. One of the most detailed modern cyclic models was developed by Paul Steinhardt and Neil Turok. It is called the ekpyrotic universe, a name drawn from the ancient Stoic concept of ekpyrosis, the periodic conflagration and renewal of the cosmos. In their model, our universe exists on a membrane, a brain in the language of string theory, a kind of sheet in a higher dimensional space. Another brain drifts nearby. Occasionally, over vast expanses of time, the two brains collide. The collision releases enormous energy, which we experience as what looks like a Big Bang. Matter and radiation flood the universe. Stars and galaxies form. Life emerges. And then, slowly, the universe expands and cools. Eventually, it thins out nearly to nothing. And then, the cycle begins again. In this picture, there is no beginning and no end. There is only cycle after cycle, each one an entire universe, each separated from the last by a collision so violent it erases all memory of what came before. The before is not nothing. It is an earlier cycle. And before that, another. Going back as far as the mathematics reaches, without any obvious starting point. This is a beautiful idea, in part because it dissolves the problem. The question of what came before becomes less urgent when there is no beginning. The universe wasn't created. It has always been cycling, always will. But cyclic models have their own challenges. Specifically, the problem of entropy. In each cycle, the universe produces disorder, entropy, and there are deep questions about whether that entropy accumulates from cycle to cycle, or whether each new cycle starts truly fresh. If entropy builds, then going far enough back, you reach a cycle so ordered it would require its own explanation. If it resets, you need a mechanism for that reset. These are hard questions, and they're the kind that scientists love. Not because they're easy, but because wrestling with them might reveal something new. String theory, one of the most ambitious attempts to unify all of physics, offers its own strange picture of what might have preceded the universe. In string theory, the fundamental constituents of reality are not point-like particles, but tiny vibrating strings of energy. Different vibration patterns correspond to different particles and forces. The theory requires not 3 dimensions of space, but 9, or in some versions, 10 or more. The extra dimensions are thought to be curled up so small that we cannot detect them. Within this framework, the notion of what we mean by the universe, by space, by time, becomes more complex. Some versions of string theory suggest that before our universe as we know it, there was a phase of string gas cosmology, a phase in which the universe was tiny, filled with a hot gas of strings, vibrating in all available dimensions. In that phase, time may have looked and behaved very differently. Space may have been indistinguishable from something we don't have a word for. The transition from that primordial string gas phase to the universe we know may be what we call the Big Bang. In this picture, the before isn't nothing. It's a phase of deep physics that we don't yet have the tools to observe directly. A warm, dense, stringy tangle of vibrating energy that predates matter, predates stars, predates space, in the form we inhabit it. The physicist and string theorist Brian Greene has written evocatively about this, about the way our universe might be one expression of a deeper mathematical reality. That reality has always been there, and always will be, in some form. Our particular universe is one bubble of clarity in a much larger sea of potential. Let's turn now to another corner of physics that has something to say about what came before. Quantum gravity. Quantum gravity is the not yet complete theory that would reconcile general relativity, Einstein's description of space, time, and gravity on large scales, with quantum mechanics, the description of the universe at its smallest scales. These two theories are both extraordinarily accurate in their own domains, but they contradict each other when applied to the same situation, such as what happens at the singularity of a black hole or at the first moment of the Big Bang. One candidate for a theory of quantum gravity is called loop quantum gravity, and it makes a striking prediction about the before. In loop quantum gravity, space is not continuous. It is made of tiny, discrete units, like atoms of space, each one unimaginably small. Time, similarly, is not smooth, but granular, and crucially in this framework, when the universe is compressed to extreme density, as it is near the Big Bang, it doesn't collapse to a singularity. Instead, the quantum nature of space creates a kind of repulsion that halts the collapse. The universe bounces. This is called the quantum bounce, or the Big Bounce. In this picture, what we call the Big Bang was actually a big bounce, the moment of maximum compression of a previous universe, which had been contracting. The contraction couldn't continue to a point because of quantum gravity, so it bounced outward, and our universe was born. Before our universe, in this model, was another universe, expanding, then contracting, then bouncing into us, and before that, another. The quantum bounce model is a cyclic cosmology too, in a sense, but driven by quantum mechanics rather than brain collisions. It shares with cyclic models the appeal of dissolving the problem of an absolute beginning. There may never have been a first moment, only a long, long chain of expanding and contracting universes, each one born from the compression of the last. One of the things that makes loop quantum gravity particularly interesting is that it may someday be testable. The quantum bounce would have left faint imprints on the cosmic microwave background, echoes of the universe that came before ours. Researchers have been analyzing the CMB data for just such signatures. The results are not yet conclusive, but the possibility that the background glow of our universe might contain whispers from before it existed is quietly extraordinary. Now let's step back from physics for a moment and think about what it means to ask the question itself. What came before the universe? There is something deeply human about this question. Children ask it. Scientists ask it. Philosophers ask it. It lives in us from very early on, this refusal to accept that there was ever simply a beginning without something behind it. We are creatures of causation. We find it almost physically uncomfortable to imagine something happening without a prior cause. And so we reach, always reach, for something behind the curtain. But there is a version of this question that is not just about physics. It is about the nature of causation itself. Aristotle, the ancient Greek philosopher who shaped Western thought for nearly 2,000 years, wrestled with this. He believed that everything that exists has a cause, but he recognized that a chain of causes can't go back forever. There must be, he argued, an unmoved mover, a first cause that itself was uncaused, something that existed without having been caused, from which everything else proceeded. This idea has been interpreted in many ways over the centuries, but its core insight is still alive in modern physics. If the universe had a beginning, what caused it? And if that cause had a cause, and so on, then either the chain goes back forever, or it stops somewhere, at something that doesn't need a cause. In some models, like Vilenkin's quantum tunneling, the universe genuinely comes from nothing, and the laws of physics themselves are part of what tunneled into existence. There is no prior cause. the laws are the cause, and they emerged with the universe. In others, like eternal inflation, there is always something prior, but that prior state is itself eternal and without a beginning, an infinite regress, not of causes and effects, but of a single, eternal, uncaused background. And then there is the no-boundary proposal, where the question itself dissolves. Time near the Big Bang curves into a kind of spatial dimension, and asking what came before is like asking what's on the surface of a sphere south of the South Pole. Nowhere, everywhere, a question without an answer, because the concept doesn't extend that far. What is remarkable is that each of these ideas, the quantum tunneling from nothing, the eternal inflation, the big bounce, the cyclic brains, the no-boundary proposal, each one is mathematically serious. Each one is the work of brilliant people working with the most precise tools our civilization has ever developed. And they don't agree, which means we don't know. And there is something wonderful about not knowing, because the not knowing keeps the question alive. And questions are some of the most beautiful things human beings produce. Let's think for a moment about what we mean by nothing. The word nothing seems clear. No thing, no stuff, no space, no time, no energy, no laws, pure absence. But physics has made nothing very complicated. In quantum mechanics, the vacuum, even the empty vacuum of space, is not truly empty. It seethes with virtual particles, pairs of matter and antimatter that flicker into existence and annihilate almost immediately. This quantum vacuum is not nothing. It is a state of lowest energy, yes, but it is still a state. It still has properties. It still has energy. It still obeys laws. When physicists talk about the universe arising from nothing, they sometimes mean this quantum vacuum, a state of minimal but non-zero energy from which a fluctuation could produce a universe. But this begs the question, as some philosophers have noted, if the quantum vacuum has properties and obeys laws, it is not truly nothing. It is something very subtle and elusive, but something nonetheless. And so the question of what was there before the universe, if the quantum vacuum was the before, becomes, what was there before the quantum vacuum? This is not just philosophical sparring. It is a genuine problem. If you want to say the universe came from nothing, you need to be clear about what you mean by nothing. And every time we specify what nothing is, we find that it has properties. And things with properties are, by most definitions, not nothing. The physicist Lawrence Krauss wrote a book with the provocative title, A Universe from Nothing. But the philosopher David Albert, reviewing it, pointed out with some force that the nothing Krauss described was actually something, a quantum field, a space-time, a set of laws. His critique was that this kind of nothing is not what most people mean by nothing, and certainly not what philosophers mean when they use the word. Krauss and Albert debated this publicly, and with some heat. And out of that debate came a useful clarification. There are different kinds of nothing. There is physical nothing, the absence of matter and energy in an otherwise existing space-time. There is metaphysical nothing, the complete absence of everything including space-time and laws. And there is quantum nothing, the lowest energy state of a quantum field. Whether the universe emerged from physical nothing, from metaphysical nothing, or from quantum nothing makes a very large difference. And the honest answer is that we're not sure which kind of nothing, if any, preceded the universe. There's another idea, less discussed but quietly fascinating. that the universe may not have emerged from nothing at all, and may not have had a beginning at all, but may have always existed in some form that we don't yet have a way to describe. This is called the block universe in one philosophical interpretation. In Einstein's theory of special relativity, time is not a separate stream that flows independently. It is woven together with space into a single fabric called spacetime. And in that fabric, past, present, and future all exist together. What we call the flow of time, the sense that the present is moving forward, may be, according to some interpretations of relativity, an illusion, a feature of consciousness rather than of reality itself. If that is true, if time is not a river but a landscape, then the question of what came before the Big Bang becomes very strange. The Big Bang is a point in the space-time block, not an event that happened in some pre-existing time. There is no before, not because time didn't exist yet, but because in the block universe, there is no privileged moment called now, no actual flow from past to future, and therefore no meaningful sense in which one event precedes another in the way we usually imagine. This doesn't answer the question so much as it reveals that the question rests on assumptions about the nature of time that may themselves be incorrect. And that is one of the most important things science does. It doesn't always give us the answer. Sometimes it shows us that the question needs to be reframed. Now, let's talk about what we do know about the earliest moments of the universe we can actually reach. Because while the true before remains elusive, the earliest detectable moments of our universe are themselves extraordinary. The cosmic microwave background radiation, the CMB, is the oldest light we can observe. It was released about 380,000 years after the Big Bang, when the universe had cooled enough for atoms to form and light to travel freely. Before that moment, the universe was a hot, dense plasma, opaque to light. The CMB is the wall beyond which we cannot see with electromagnetic radiation, but it contains information. Its temperature fluctuations, tiny variations in warmth from one part of the sky to another, are the seeds from which all structure in the universe grew. Galaxies, clusters, superclusters, the great cosmic web. All of it traced back to those tiny fluctuations imprinted in the CMB like a fingerprint of the early universe. And within those fluctuations, some cosmologists believe are echoes of what came before. If the universe went through a big bounce, the structure of the CMB might carry faint memories of the previous contracting phase. If inflation happened, the CMB should show specific patterns of polarization called B-modes, which would be evidence of primordial gravitational waves generated during that inflationary burst. The search for B-modes in the CMB is one of the great experimental endeavors of modern cosmology. Several experiments, both on the ground and in space, have looked for them. Some hints have appeared. Some have been revised away. The search continues. We may, within a generation, find the first physical evidence of what the universe was doing before the earliest moment we can currently see. Not what was before the universe, perhaps, but what the universe was doing in its very first instant, before it became what the CMB shows us. And that would be a profound thing. There is a concept in cosmology called the Planck epoch. It is the first 10 to the power of negative 43 seconds after the Big Bang, a number so small it barely fits inside a thought. In that interval, the universe was so hot, so dense, so energetic that all four fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, were unified into a single force. We don't know what that unified force looked like. We don't have a theory that describes it. Before the Planck epoch, our physics stops working. The equations break down. They produce infinities where they should produce numbers. And infinities, in physics, are usually a sign that a theory has reached its limits, that something new is needed. What lies behind the Planck wall is, in a deep sense, the edge of what physics can currently say. It's not quite the beginning of the universe, but it's the beginning of what the universe can tell us about itself. Some physicists call this the trans-Planckian problem, the question of what happened before the Planck time. And while various theories, loop quantum gravity, string theory, and others, attempt to extend into that regime, none have been confirmed. We are standing in this sense at the frontier. And frontiers are beautiful. There's one more idea worth sitting with before we begin to drift towards sleep. It is one of the most radical proposals in modern physics, and also one of the most poetic. It comes from the work of physicist Julian Barber and others who have thought carefully about the nature of time. Barber has argued, with great mathematical rigor, that time does not fundamentally exist, that what we call the flow of time is not a feature of the universe, but a feature of the way we experience it. In his framework, the universe is better described as a collection of static configurations, moments that exist without any intrinsic order or sequence. What we experience as the passage of time is the mind constructing a narrative from those configurations, a story of before and after imposed on a reality that may have no such structure. If Barber is right, then the question of what came before the universe doesn't just dissolve. It was never quite the right question to begin with. There is no before and after in any absolute sense. There is only the arrangement of things, and the universe is one arrangement, or rather, an infinite collection of arrangements, none more prior than any other. This is not a comforting idea if you need things to be clear, but it has a strange restfulness to it, too. The idea that time might be something we make rather than something that happens to us, that the story of before and after is a story we tell, a beautiful, necessary fiction that allows us to navigate the world but doesn't necessarily reflect the deepest structure of reality. In 2023, physicist Nima Arkani Hamed and his collaborators proposed something called amplituhedron and related structures, which suggest that space-time itself might be emergent, that it arises from something deeper, a mathematical structure involving no space, no time, and no particles as fundamental ingredients. In this view, what we call space and time are not the bedrock of reality, but the foam on its surface. Beneath that foam is something stranger, something without a before or after at all. These ideas are speculative. They are not yet complete theories, but they point in a direction that many physicists find compelling. The direction toward a reality more fundamental than space and time. A reality in which the question of what came before the universe is not so much unanswerable as it is asked in the wrong language. The right question might not be, what was there before? But rather, what is it that gives rise to space and time at all? And what might that be like when it doesn't yet contain them? We don't know. And there is, as I said at the beginning, something wonderful about that. for all the sophistication of our instruments, for all the elegance of our mathematics, for all the centuries of thought that have gone into these questions. The deepest one remains open. The before is still dark, still quiet, still full of possibility. And that darkness is not a failure. It is an invitation. Every great discovery in the history of science began as a question that seemed too large to answer. The motion of the planets, the nature of light, the structure of matter, the shape of space. Each one seemed at some point beyond reach. And then, gently, patiently, the universe allowed us a little further in. We are not done. We are not even close to done. There will come a day, perhaps a long time from now, perhaps surprisingly soon, when something new is found in the CMB, or in a gravitational wave detector, or in an experiment no one has yet designed, that will pull back one more layer of the before. That will show us something of what the universe was doing before we could see it. And when that happens, it won't end the mystery. It will deepen it. It always deepens it. Every answer in science opens onto a larger question. That is not a flaw. That is the nature of an infinite subject encountered by finite minds who are curious enough to keep looking. Tonight, you've heard about a physicist who proposed the universe could tunnel from nothing, carrying its own laws into existence. You've heard about membranes colliding in higher dimensions, generating big bangs that look to us like absolute beginnings, but are, in the larger picture, just another beat in an ancient rhythm. You've heard about a universe that might bounce forever, each contraction giving way to a new expansion. About time that might curve into a kind of space near the beginning, removing the possibility of a before entirely. About a quantum vacuum that seethes with potential. About a block universe where past and future are as real as the present. About a reality beneath space-time itself, from which space and time emerge like foam from a deeper ocean. None of these ideas contradict each other in the way that scientific theories sometimes do. Most of them are not yet testable. They are, in this moment, more like landscapes of possibility. Beautiful, rigorous, mathematically serious possibility. Each one a different vision of the same deep mystery. And sitting with them, letting them drift through the mind as the body grows heavier and the eyes grow softer, is its own kind of rest. Because these questions ask nothing of you. They don't require resolution. They don't need to be solved tonight. They are old questions, older than science, and they will still be here tomorrow, patient and luminous, waiting for the next person brave enough to ask. You are part of this story too, not just in the sense that the atoms in your body were forged in stars, though they were, but in the sense that you are the part of the universe that is curious about itself. You are the way the cosmos holds a question about its own beginning. And that is not a small thing. The universe has been expanding for nearly 14 billion years. Stars have formed and died and formed again. Galaxies have collided and merged. Black holes have grown and spun in silence. And somewhere along the way, on a small planet orbiting an unremarkable star on the edge of a middling spira galaxy, something happened that had never happened before anywhere we can see. Matter became aware of itself, and it started asking why. That asking is ancient. It lives in the cave paintings and in the cathedrals and in the equations written on chalkboards. in the cold light of late nights. It lives in children who look up and wonder, in scientists who spend their lives reaching for something just beyond reach. And it lives in you, tonight, in the soft space between waking and sleep, where the largest questions feel not terrifying, but gentle, like the universe itself leaning in to whisper that it, too, doesn't entirely know. But it's glad to have something inside it that keeps asking. The stars are still out there. The CMB is still glowing, faint and ancient, all around you. Dark matter is drifting through the room right now, passing through your body without leaving a trace. Gravitational waves from distant collisions are stretching and compressing the fabric of space in amounts too small to feel but real nonetheless. The universe is not quiet. It is full of motion, full of remnants, full of echoes from before. Some of those echoes reach back further than we can yet read, but they are there. And tomorrow, or next year, or in the lifetime of someone not yet born, one of those echoes might finally speak clearly enough to be heard. Might give us one more piece of the answer to the oldest question we know how to ask. Until then, we rest with the mystery. Not because we have given up, but because rest and wonder are not opposites. They can coexist perfectly in a mind that has learned to love the question as much as any answer. So let your thoughts slow now. Let the ideas that have drifted through your mind tonight settle like dust in still air. The cyclic universes, the quantum foam, the bouncing cosmos, the eternal inflation, the no boundary space, the block of time where past and future coexist. Let them settle gently. You have been, for this little while, somewhere near the edge of what we know. That is a remarkable place to visit, and it is a very peaceful place to leave from as sleep begins to come. The universe will keep its questions a little longer. They are in good hands. They are in the hands of curious people on a small planet, looking up and wondering, as they always have, as they always will. If these quiet journeys through science and mystery help you rest, or spark the kind of curiosity that follows you gently into your dreams, consider liking this video and subscribing to the channel. It helps other sleepy, wondering minds find their way here, one peaceful night at a time. And now, as the questions soften into something wordless, and the stars continue doing whatever stars do in the dark, let yourself drift. Let the universe hold the before, and let sleep hold you. Good night.